Hello, my name is Noah, and I, along with Diril, Shri, Persia, and Kashyap, have analyzed and redesigned a gripper of a robotic arm. A robotic arm's gripper holds and releases an object that the arm would like to move either for placement or inspection. It typically has four components of base, wrist, clamping gears or linkages, and the gripper tips. Our primary customers are the automotive industry for situations when they need to manipulate small parts like bushings. Our secondary customers are the medical and cosmetic industry, who often have to move small tiny vials. We expect in total to produce 150,000 units. Here's an exploded view of our gripper. The size and base plate combine to house a servo in the back. Similarly, the upper and lower wrist plate and connector house the wrist servo and attached to that other servo. And finally, the grippers are attached to the claw gears, and then the wrist connector plate is screwed onto the servo. Here's a fast diagram for our gripper. We would like to move the object, so we handle the object by holding or releasing it. We guide the object by controlling its Z rotation and controlling its speed. We assure dependability by securing the object by controlling clamping force, maintaining orientation, and increasing stability of our gripper. We assure convenience by enabling mounting to external mechanisms, and we enhance the product by customizing gripping, by customizing the softness at the tips, or customizing the clamping force. We considered two possible assembly sequences, the first starting with the central base plate, and the second going from back to front beginning with a side plate. Overall, we determined the second sequence to be preferred mainly because of its ease of testing subassemblies. We then mapped the functions from our FAST to the parts of our gripper. As you can see, the side plates enable mounting to an external mechanism, and the claw gears and gripper subassemblies guarantee holding and releasing an object.
The bill of materials shows the rough cost estimates for all the components in the robotic arm gripper, including the fasteners. As you can see, the total cost comes to $44.68. The quad chart classifies the main components, excluding the fasteners, based on their manufacturing cost, acquired through the bill of materials, and functional importance through function component mapping matrix. As demonstrated, we have multiple potential components for redesign purposes, besides the elimination option for the wrist connector. With respect to product family design, the differentiation table shows that customizing softness and customizing clamping force are the two functions which are different for each product variant. With respect to component commonality, we can see that clamp servo motor and the right and left grippers are considered to be module components. They serve the differentiated functions as discussed before and are different for each variant. The remaining components are considered as platforms, and they are common between the two variants. Module components and their variants are demonstrated in this slide. Stall torque is the factor which differentiates the servo motors and makes each suitable for the respective customer group. Also, the different tip shape for each gripper variant accommodates the gripping needs of our two customer groups. This slide shows the common interfaces between our module variants and the platform parts. Both grippers attach to the claws through identical holes with fasteners. Also, both clamp servo motors are identical in size and hole placement, so they are also attached to the platform identically with fasteners. The original assembly diagram portrays the aforementioned selected fishbone sequence. However, shifting platform components earlier in the assembly sequence will let us delay the assembly of module variants and enhance our assembly sequence for delayed differentiation.
In the assembly sequence in the product family assembly diagram, we perform the assembly analysis of the primary product variant to calculate the total assembly time and assembly efficiency for manual assembly. The total assembly time is 325 seconds and the efficiency is at 8.3%. We have selected the wrist plate as a platform part and the gripper as a module part for redesigning, which had relatively high assembly time compared to other parts. And you would see the same parts in the high quadrant in the quad chart as well. Redesign of the wrist plate, which is the platform part, you would see DFA-1, which is reduced part count, going from 3 parts to 1 part, and DFA-2, reduce or remove fasteners to reduce the assembly time, and DFA-13, avoid adjustment of parts by eliminating redundant part assemblies. Redesign of the gripper, which is the module part, you would see DFA-2, reduce the fastener part count from 6 fasteners to 4 fasteners, DFA-6, increase part symmetry by centering the key slot on the gripper, DFA-10, tighter fit with the key slot for better insertion. The redesign for manual assembly, the total assembly time comes down to 134.1 seconds and the assembly efficiency increases to 13.4%. Design for manual assembly, the summary is the total assembly time comes down by 190 seconds and efficiency increases by 5.1%. In the primary product variant, after design for manual assembly and based on the assembly sequence in the product family assembly diagram, we have selected the base plate subassembly involving 3 small lightweight parts for which high-speed automatic feeding, orienting, and insertion can be utilized to reduce the assembly cost. You would see these parts in the high quadrant in the quad chart as well, which is for redesign. The total assembly cost comes to $9.03 after the analysis. Design of the base plate assembly, you would see we followed reduce part count, which is DFA1, going from 3 parts to 1 part, and reduce and remove fasteners to reduce assembly time, which is DFA2, and allow hand and tool access by removing the step from the front, which allows better handling and tool access, which is DFA4. Redesign analysis for the base plate assembly shows the total assembly cost comes down to $3.05. Summary for design for automated assembly, after the redesign, you would see the total number of parts went down from 9 to 1, and the total assembly cost went from $9 to $3.05.
Process selection for wrist connector, sheet metal working, and machining are the two manufacturing processes that are feasible for the manufacturing of wrist connector. Process selection, gripper manufacturing. Injection molding is the manufacturing process that is feasible for production of grippers. After process selection, sheet metal working was considered as the feasible process to manufacture wrist connectors. DFM was conducted and the calculations were done as shown in the slide. The total cost of sheet metal working was 0.29 cents per part. Redesign of wrist connector was done based on the suggestions from DFM Pro and with the help of DFM sheet metal working guidelines. The left side shows the before redesign part and the right side shows the after redesign part. The before and after redesign cost of wrist connector is shown in the table. According to the analytical method, 29 cents were the cost for before redesign, which dropped to 26 cents after redesign, and on the hubs it was around 13 cents for the before redesign and 11 cents for the after. After process selection, injection molding was considered as the most feasible option to manufacture grippers. According to the DFM calculations, injection molding cost for the grippers is around 14 cents. The redesign of injection molding part, that is gripper, was done based on the suggestions given by DFM Pro, and the callouts show the DFM guidelines that were also employed for the redesign of gripper. The before and after redesign cost of the gripper doesn't change much because of the recommendations from DFM Pro do not significantly impact on the design, and thus the total cost of the part more or less remains on 14 cents.
Services and warranty. Service contracts are agreed upon during the time of purchase, and all the parts necessary for repairs are covered for free. Technical support is available by various means, and if travel to a location is required to fix an issue, then all the parts are covered for free, but the labor and travel expenses are still billed. Failure due to abuse and neglect is not covered by warranty, nor is downtime and related costs due to failure. All parts to be returned must be sent in reusable shipping boxes. Ways to improve the customer service experience would be to have automatic notifications related to equipment maintenance and a customer portal for customers to find all order-related information. In conclusion, the gains of the DFM are an overall cost reduction of $5.99, a reduction in number of parts from 6 to 2, an increased manual assembly efficiency, and a decreased automated assembly cost by $5.97. The pros are that the assembly of the part is easier due to removal of fasteners and lesser number of parts, but the cons are that the metal working parts are small, so the process would have to be very delicate. And in a practical scenario, we would have to use CNC machining or laser cutting for holes. In hindsight, we should have considered a single platform splitting the left and right grippers so that only the ends of the grippers could be modified for different applications, allowing for delayed differentiation.